Good morning, students. I am Vikram Singh Rathod, Assistant Professor at Center for E-Governance. Today I am representing the decision tree in machine learning. In this topic, I previously make a program related to SVM model, and in this lecture I am define the decision trees, a versatile machine learning algorithm that can perform both classification and regression tasks and even multiple outputs tasks. They are very powerful algorithm capable of fitting complex data sets. For example, in previous e-lecture, you trained a regressor model on the California housing dataset fitting it perfectly, actually, or fitting it. In our previous lecture, I am describing about regressor model, a logit model, or a SVM model. You can also notice that and also practice on the above codes. And today I am represent the decision tree codes for you for making the programs. Basically, the decision tree are also the fundamental component of random forests, which are among the most powerful machine learning algorithm available today. In this e-lecture, we will start by discussing how to train, visualize and make prediction with decision tree. Then we will go through the CART training algorithm by using scikit-learn. Scikit-learn is a library you well known, and we will discuss how to regularize trees and use them for regression tasks. Finally, we will discuss some of the limitation of decision tree. Training and visualization of a decision tree. To understand decision tree, let us just build one and take a look at how it makes prediction. The following code contain a decision tree classifier. It is basically a class that is imported from sklearn library on the iris dataset. I am giving you an example. For example, first of all, I am call the sklearn using from keyword from sklearn dot dataset, then import load iris. You understand that the sklearn is a library and dataset is its method, and then import the data that is being used in our program for the decision tree concepts. So I am defining here load iris. It means the database of iris is imported in our program. From sklearn.tree, import decision tree classifier. In this line, you can understand that the sklearn a library and a tree is its method or a function. Through by it, we can import the decision tree classifier that is used in our coding for decision tree concepts, and then I am defining a variable iris is equal to load iris. So here the iris is a variable and it hold the complete data of iris data set, and then I am defining the x variable is equal to iris dot data, and then defining the slicing method of listing colon comma 2 and then colon for the petal length and the width that is used to store in x variable, and then I am create a y variable is equal to iris dot target. It means target or data is the field value of our iris database or a data set. Then I am create another variable tree underscore classifier CLF is equal to, and then I put here decision tree classifier and then put the argument as a max depth is equal to 2, and then tree underscore classifier dot fit x argument x variable and y variable. After executing this program, the some output is giving to you in our next slide. You can notice that the field values, those are belongs to decision tree classifier. You can see after executing the above code, the decision tree classifier put some values, give some values as those are the field values in decision classifier tree classifier dataset, such as class underscore weight is equal to none, and creation is equal to Genie, and max depth is equal to 2, max feature is equal to none, max leaf node is equal to none, and min impurity underscore decrease is equal to 0.0, min impurity split is equal to none, and min sample underscore leaf is equal to 1, and min sample split is equal to 2, and min weight underscore fraction underscore leaf is equal to 0.0, pre-sort is equal to false, random state is equal to none, and splitter is equal to best. These all are the values, those are stored in our decision tree classifier dataset. So output you can see in the slide, and also the value as per defined in the decision tree classifier. Here I am also put you a running code using Anaconda Spider tool. I am run the previous code that is defining our slide and executing. The output is showing you this slide. The output is as per I am previous described the slides. You can see, notice for your convenience, you can also use Anaconda environment and use a Jupyter tool as well as a Spider tool or anything those which you may convenient. You can run the program as per given in this slide. You can visualize the trained decision tree by first using the export underscore graph viz method to output a graph definition file called iris underscore tree dot from sklearn dot tree import export graph viz. Here I am describe you that the sklearn is a library and tree is a method, and that import the export graphic viz export underscore graphic viz tree, a file that is hold a picture of a decision tree. As I am defining here, tree underscore classifier out underscore file is equal to image path, and then putting the path where the iris tree dot file is stored, and then the feature name iris dot feature underscore name colon 2, then the class underscore name is equal to iris dot target names, and rounded is equal to true, and filled is equal to true. After execution of this code, a picture is represented you, and you can specify the outputs of this code. Then you can convert this dot file into a variety of formats such as PDF or PNG using the dot command line tool from the GraphicViz package 1. This command line convert the dot file into PNG image, so you can also convert this file into a PNG image. Writing here I am code dot dash tpng iris underscore tree dot dot minus o iris underscore tree dot png. It convert the tree dot file to iris underscore tree dot png. Your first decision tree looks like figure in this our lecture. As per the decision tree, I am defining a slide here. The values those are used in our codes such as petal length is equal to less than or equal to 2.45, Gini is equal to 0.667, sample is equal to 150, and value is equal to 50, 50 and 50, and class is equal to setosa. Basically it is a condition that is run by the decision tree algorithm. So I am putting here the two concepts. If the condition is true and the Gini is equal to 0.0, sample is equal to 50, and value is equal to 50, 00, and class is equal to setosa. At the end of the true, it is exit from the program. And the another hand, if the condition is false, then the output is petal width in centimeters less than equals to 1.75, and Gini is equal to 0.5, and sample is equal to 100, value is equal to 0, 50, 50, and class is equal to vesicolor. And that is further divided into two parts as per decision tree concepts. The values are given in the set. Gini is equal to 0.168, and sample is equal to 54, and value is equal to 0, 49, 5, and class is equal to versicolor. And another the part of the decision tree of iris dataset, the values are Gini is equal to 0.0425, sample is equal to 46, value is equal to 0, 1, 45, class is equal to Virginica. These all are the values that is depending upon the concept behind the decision tree executing the program. And then after I am defining how to making prediction. You can see in the previous slide a tree represented in figure 6.1 mark prediction. Suppose you find an iris flower and you want to classify it. You start at the root node, depth 0 at the top. This node asks whether the flower is petal length is smaller than 2.45 centimeter. If it is, then you move down to the root left child node, depth is equal to 1 comma left. In this case it is a leaf node, such as it does not have any children node, so it does not ask any question. You can simply look at the prediction class for the node, and the decision tree predicts that your flowers is an iris setosa, class setosa. As per our previous slide, you can notice that a true condition, if the condition is true, the following values are, you can notice in this slide. And now suppose you find another flower, but this time the petal length is greater than 2.45 centimeter. You must move down the route, right child node depth is equal to 1 comma right, which is not a leaf node. So it is asked another question: is the petal width smaller than 1.75 centimeter? If it is, then your flower is most likely an iris. Vesicular is equal to depth is equal to 2 left. If not, it is likely an iris virginica. Depth to right. It is really that simple. A node samples attributes counts how many training instants it applies. For example, 100 training instants have a petal length greater than 2.45 centimeter and depth is equal to 1 and right, among which 54 have a petal width smaller than 1.75 centimeter and depth is equal to 2 and left side. A node value attribute tell you how many training instants of each class this node applied to. For example, the bottom right node applied to 0 iris setosa and 1 iris versicolor and 45 iris virginica. Finally, a node Guinea attributes measure its impurity. A node is pure Guinea is equal to 0 if all training instants it applied to belong to the same class. For example, since the depth 1 and left node apply only to iris setosa training instance, it is pure and its Gini score is 0. So you can notice that here I am defining a graphical representation of decision tree boundaries, such as x-axis as a petal length and y-axis as a petal width from 0 to 3 and the x-axis is 0 to 7. You can notice that the three partition is divided in this graph. The depth is equal to 0, that defines some values 1 to 2, and the depth is equal to 1, defining dash line and defining depth to value in blue color, and then after 5 to 7 defining some triangle values of green type values from 5 to 7 decision boundary. In figure you can show that the decision tree boundaries, the thick vertical line represent the decision boundary of the root node depth 0 and petal length is equal to 2.45 centimeter. Since the left area is pure only iris setosa, it cannot be split any further. However, the right area is improved, so the depth 1 right node split it at petal width is equal to 1.75 centimeter represented by the dashed line. Since max underscore depth was set to 2, the decision tree stops right there. However, if you set the max depth is equal to 3, then the 2 depth 2 node would each add another decision boundary represented by the dotted lines. Thanks, students.